Okay, so what are you trying? Why are you multiplying?
Because like I said, we are trying to get ratios at each point. And to get when let's say the probabilities are ratios of
The probabilities are not ratios.
okay, okay, what I mean by, maybe I'm not using the right word.
Okay.
What I mean by ratios is that, like,
Okay, wait. Good. The term is proportion.
Yeah.
Good. Okay. Yes. So let's say I have a football match for a team. So they are going to play 10 matches. And I'm saying that each match outcome is, let's say, a Bernoulli. Right? Okay. And then I say find the likelihood function. So each match is a trial, right? Yes. How are you?
Bernoulli, for instance, it has, like you said, it has two outcomes.
Yeah.
A win or a loss.
Mm.
Right?
Yeah.
So each one will be 1 over n. Like
1 over n, no?
1 over 1, because there are two outcomes, it will be 1 over 2.
Mm.
Yeah?
1 over 2, it can be. I can also say that this team is just like maybe maybe Kotoko is going to play against a Division 4 team. Then Kotoko has they have more chance of what? Scoring that team. Because of course they have played together, they have better facility. The Division 4 team, they will just be, okay, I've come back from, it's just like the Saturday ball we all go to play. Right? So there's no cohesion and so forth. So we can say that there's a 90% chance of Kotoko winning. That cannot be 1 over 2. Okay, but my main thing is, why are you multiplying? That's the key thing. You are forgetting something. In that you are assuming that they are independent. If two events or trials are independent, then they are joint occurring. So the likelihood is just a joint occurrence of all of them. So the fact that I say this will be a win, this will be failure, or loss, win, 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 loss, loss. What is the joint occurrence of all this? That will be the product of all of them, because we are assuming that the outcome of this match does not have any influence on the next and the next and so forth. Okay. And then you say, well, we sum all of them. Why are you summing? Because we said find the log likelihood. If you find a log likelihood, then this product now become what? Summation. Is that okay? Now, why do we use the log likelihood? So now it's like we are doing the, what is it?
The
comprehensive, like the oral. Because we can, it's just like we are talking, we just want to see on the polls, how do you really understand statistics and how you can explain.
Then we have to. Then I have to attend on them.
The level,
But
you,
100 to 400.
yeah, but I mean, if you are up there, you should be able to, because as of now, we should be able to employ you to teach.
Yeah, it's true.
So it's that sort of interaction we have with you.
Okay.
On few occasions, will we say go to the board, and because we do it at the other place. Linearize. Because it's log. You have a point there, but that's not really the issue. No, so whatever you are learning, understand the basics, that's all.
Okay.
No, we've forgotten some of them.
So you revise.
You need to go and revise.
You have to revise.
That's all we get.
You have a
The
statistics.
Yeah.
You have to join the 1100.
You can. I mean, nobody is.
But when you don't, you only need the slides. You just
Yes, it's not really like you see the computation itself will be an exam that we want to. Yes, but when you go out or somebody if you are at the workplace, what they are asking you are basic stuff. So you can't, and that's what we want to find out whether overall you really understand the concepts and so forth. Yeah. So that's it. Yes. Okay. So why? So this one we can ask you quite easily.
What is maximum likely estimate? Oh, I know it to explain it to a layman.
Yeah. So we find log likely. Why do we find log likely and not just the likelihood? So it's simple. Because the main thing is that when you find logs, it becomes easier. You see, if you are doing something and you are doing multiplication,
you are multiplying
many. Yes, so when you find log, it becomes, so it makes it a bit easier to handle. But the key thing is that we say maximum likelihood. So what maximizes the likelihood function? So it turns out that whatever will maximize the log likelihood automatically maximizes the likelihood function. So it's the same. In other ways, we are getting the same thing, but I find an easier way of what.
So, Prof, that's why it becomes a summation of the.
It becomes summation. Then you use it. So at this level, yes, there are complications in what you are doing, but you should now understand the basis so that you can begin to talk about statistics wherever you find yourself. So that's it. And it makes it easier for you to understand some of these concepts. So the concept we've talked about, now we talk about maximum. How do we find the maximum? Remember we said likelihood function and you are finding the maximum of the likelihood function. So what do you do to find the maximum likelihood? You have a function, you want to find the maximum, what do you do? You add. No, that will not give you.
The maximum.
Yes, I give you a function. I say find the maximum. A mathematical function. Yes, it can be if it is discrete, the highest frequency. Yes, but how do you find it? If I give you a function, of course you are not going to point to say you can point that this is the maximum. But how do you find it mathematically? When you differentiate it, yes. Zero, yes. Is that is it only the maximum? Is it only the maximum? dy dx is equal to 0. Is it, does it? It can be the maximum, it can be the minimum. Good, okay. So the key thing, now you know why. If we are differentiating, you know what is the reason. Because we want to find the maximum. So ideally, when you find dy dx is equal to 0, we are supposed to now check the second derivative to check whether it's less than 0. Then that gives us a maximum. Okay. Now it turns out that in R, we won't be, all the routines we use for this finds the minimum. But we want maximum. So what do you think we have to do to get the maximum? R is giving you the minimum point. So how do you find your maximum?
So the minimum point from 1, when you subtract from 1, becomes whatever is there with the maximum.
Are you sure? No, the one manager will give you a compliment if it's a probability. That cannot be the maximum.
Okay, well, it's
Okay, so you see, some of these things you have to think through and see what really we want. So, yes, so it's from the basis, just the basis.
No, the basis, the problem is that the basis we left it for long.
No, you don't have to. So what is happening is that, you see, I have a function, I want the maximum. R only gives me minimum. So what do I do? Inverse
So
will
you
not.
Inverse.
You turn it. If it is symmetric, you can do so. Yeah, but you can turn it. So how do I turn it around like this?
Find the inverse.
No, the inverse will not. So you see, if something is positive and I find the maximum, if I want that maximum, I can also negate it. If I negate it, it will come this way.
Yes.
Oh, yeah.
Yes.
So I negate it and I find the minimum. That is my maximum. Because the higher it is, if I negate it, it becomes very small.
Yeah.
Let's say that, let's say 1.
Yes.
If you have negative 1.
Yes.
And the maximum of negative 1 is negated, it becomes 1.
The minimum of the negative
Yeah,
one. Yes.
Minimum is.
Yes. So if I have the function, then the highest point is 1, right?
Yeah.
And then I turn it around like this. The negative one becomes the minimum point. So if I find the minimum point of the negative of the function, that gives me the maximum point. So that's the sort of thing we will be using in R. So if you see that we have negative log likelihood, then it means we have negated the likelihood function, and then we are finding the minimum of it. That becomes our maximum value.
No, Prof, you mentioned that if we negate it, then we are finding the maximum.
No,
So
we
by default,
occasion no.
log is-
We want the maximum. That's why it's maximum likelihood. Okay, the routines in R are minimization problem. Yeah, but because of this relationship between the minimum and maximum, you won't see maximum. Usually it will be minimum. So what do? You negate your function, you find the minimum, and that's the maximum point. That's it. Actually, we are finding the value that will give us or the maximum point. So the value that gives you the minimum point of the negation is the same. Right. So that's the sort of thing we will be doing at the maximum likelihood. So it means that for us to implement maximum likelihood within a likelihood function, and if you go to your undergraduate and so forth, every function you can find the likelihood by what? Multiply either the PMF or what? The PDF. Okay, so let's look at an example. Now for the gamma, we can write the gamma PDF, right? Okay. Now, if you check here, I did in R, it's like this. But what we did will be the sigma is equal to 1 over. We've changed it the other way around. So our the alpha is our beta, right? The way I wrote it, okay. Alpha is our beta, and then the scale is our alpha. Yeah, but so we'll get beta, or sigma is our beta, so to speak. Alpha is okay. Okay. So because we need this place should be negative beta x. That's the exponential part. Right? Okay, because it's 1 over that. Okay. So now, if I want to do this, it's the product of this fxi. Right? Okay, then I find a log likelihood, it will be what? Summation of that. Is that okay? Which means the x in there will be x1, x2, x3, and so far to xn. Okay. So if I want to write a likelihood function for this, I can. Is that okay? Yeah, and I can get a log likelihood as well, which will be the summation of log of all this. So how do I do that? So log like, okay, will then be a function. And this function, what does it take? It will take x. X will be the data. Okay. Then I need, in our case, we need alpha, right? And then we need what? Beta. Is that okay? It needs this to work with. Okay. Then I can open this. So we need to do the sum. The
Prof,
yes.
since we are choosing to call it log, like LOG.
Yes, we are giving yes, yeah, log. Okay, maybe log like I made a mistake. But it doesn't matter, you can give it any name. So L like will be equal to, remember we say sum, right? Because we are going to do sum, right? And then we need log, right? Sum log, because we are using the log likelihood, right? Then we need to write what is here within that function. There are two ways to do this. I can also use, because the density, so I can also use d norm. Oh, sorry, d gamma, which is also the density. Yes? Okay. So this one, I need to write this.
I don't know the densities of all the
Yes, yeah, once it's written. But I'm doing this because in the paper that I gave you, you don't have an explicit density, or you won't find it in R. So this, what I'm doing is a general form. But if R knows it already, I can just put in D gamma and go my way.
So where it doesn't know that one?
Yes, yeah, you use the, you have to write the function on your own. Okay. So this one, the top one will be beta raised to the power alpha. If you remember your gamma, that's what beta raised to the power alpha divided by gamma alpha, right? And then we have x raised to the power alpha minus 1, and then e to the power negative beta x. That's what we are going to do. Okay. So let's see. So the first one will be beta raised to the power alpha. You have to be careful with the parentheses, okay? Otherwise, you'll get them wrong. Divided by, then that is a gamma. Gamma is also the special function for mathematics. So gamma, and then I put in what? Alpha. Okay, so even these ones, if I'm doing it, I will just be using capital to distinguish it from what is inside R. Yeah, but it's okay. Then I go outside this. So log of all that. So whatever I'm doing should be within the log. Yes.
You see, gamma, like you said,
Gamma is this one, no? Gamma alpha. Yeah, it's a function.
R knows it as a function.
Yes, I know the
Knows
gamma.
it as a function. How about when you are now using the symbol and not the function, like the gamma symbol?
Yeah, so it means that when you have to get, you see, I wrote over here, but it's a comment. Yeah, so if I had used this to name something, there will be a conflict. R doesn't know whether it's a function or the inbuilt function, so you have to be alert on some of these things. That's why I was saying that this, we should maybe make it beta like this, so that it distinguishes from what I will store it in there. So in that case, all this will be alpha, and then beta, like this. Okay, and then this one is alpha, like that. Okay, then within the log, we also have x to the power alpha minus 1. So all of this, so I can put all this. If you are doing this, as I said, you have to be very careful with the parentheses, otherwise you get it wrong. So now x raised to the power what? And then that should be in curly bracket, alpha minus 1. Minus 1. Okay, then I go outside, and then I multiply that by what? ESP, and then it is what? Negative beta times what? Times x. Times x. So that's my likelihood function. Okay. When I'm returning this, I'll return it with what? Oh, did we? I think I did not. Instead of I've come up. I need to do it now. Okay. So when I'm returning it, remember what so I'll return what? Negative log like. Is that okay? So that whatever we are going to do will be what? The maximum. Okay.
So, I don't understand what you mean by return. Can you explain that?
Which one?
Return.
So remember we said we are going to use negative. We are going to find the minimum of the negative, then it becomes, so that's why I'm returning the minimum, the negative.
Yeah, that one understand, but when you use
Return. So that's the output.
okay.
If we put x, alpha, and beta in there, it should give us the product.
Okay. So that indirectly commanding that issue.
Yeah, calculate the likelihood, the log likelihood. That's it. Is everybody okay with this? Okay, good. Okay. So once we do this, so this is log likelihood function. Log likelihood function. Okay. Then here the next thing we will do is to optimize the likelihood function. On the data. So I asked you this question: what is maximum likelihood? Well, what it says is that the likelihood principle says that if I have a data set, the maximum likelihood estimate, okay, are the estimate of the parameter within the parameter space that will give us the highest probability of producing that data. So if we take that definition, then it means that if we have a data set, we will put our maximum, the log likelihood on it. Each combination of, in this case, alpha and beta will give us a likelihood function. The one that will give us the minimum value will be the most appropriate estimate for that data. And that's the maximum likelihood estimate. Minimum, because now we are using the negative likelihood. Yeah. But that same value is the maximum. That's the concept. So how do we optimize our function on the data? That's an optimization problem. And that's like when you find your dy dx is equal to 0, you are finding the zeros of that function that will make it, that's it. So it means we need some optimization, like the Newton's method. The minimum one or the common one is the Newton's method. You can do the bisection method. There are a whole lot of this, secant method and so forth. All those things are part. And that's I mean a huge research area, optimization, because it has so many uses. So that's the sort of thing. In R, the basic one is called, the basic routine is optim. Optim. So let's see. So it says general purpose of optimization. So general purpose optimization based on Nelda-Mead is an optimization of quasi-Newton. I talk about Newton methods. Conjugate gradient of a whole lot. Okay, so how do we do this? Well, the usage is like this. So we will copy this, and then I'll show you how we can do this. So the power, maximum likelihood, the problem with maximum likelihood is this. Even though I don't know the parameter, I must give it a guess to start with, because it's a set algorithm. That the bisection method. you have to take A and B such that you know that they will contain what you are looking for. If it is on this side, it will not be good because you won't find your solution. So always you can look at the sign of the function to help you choose such that the zeros of that function will be within this A and B. And so forth. Okay, so it's the same principle here. But we don't know, so you have to choose some value. So for example, you see we generated the data from the gamma distribution with 5 and 4. We don't know, so we are going to choose, let's say, maybe 2 and, let's say 2 and 2. 2 is, okay, so let's say 2 and 4. We are outside it, but it will iterate and come back to whatever. But the closer your guess is to the parameter, the easier it is for the function to converge. Other than that, it has to run so many iterations to get to that point. The iteration is what you used to do in math, second year or third year math, and or first year math at the university. That Newton's method, you do this, you iterate. That's the same thing we do over here. Okay, so here we need some, and these are 2 parameters, so we need estimates for them. And we are saying we are going to use maybe 2 and 3. So alpha is 2, beta is 3. Is that okay? This one we know the parameter, that's why we are choosing something close to, but I can choose 10, 10, and it's going to iterate out until it comes. It's just a guess. But I mean, if you are doing this in practice, we usually will use the moment estimator. The moment estimator is good, but it's not that efficient. So it gives you something that is scientific, not guessing, right? And then I now improve upon it with this estimate. That one, I mean, it's like you have to go through another method. We can use, let's say, goodness of fit test, okay, to find this, but I mean, you are going too far. So usually in this kind of, any value you give it, because they iterate about 10,000 times. So if it is not too far, you will still come to it. Or it will get to a point where it gets you the minimum, but that's the minimum after the 10,000 trials, because we cannot move on again. Yeah, so that's it. But it will tell you, the output will tell you that it did not converge, but the iteration, the number of iteration has elapsed. So this is the minimum I can give you. That's the sort of thing we do. Okay. Then the function is the function you want to optimize. In this case, it's what? The log-like. So, and this one, GR is gradient. And all this I'm saying is down here. So parameter is what? Initial values of the parameters to be optimized over. So you have to give a starting point. Fn is a function to be maximized. So you remember that is the function we want to maximize. Good. Okay. GR is the gradient. You can differentiate the function in R to get a gradient. R does differentiation as well. Yeah, but I mean, it's not needed. It can be done throughout, so it can be done. So we are not providing any gradient for the function. I will do that automatically. But if we have the gradient, you can put because we can differentiate the function and also get the gradient. Yeah. Usually, if you are doing some optimization and the function is large, then if you provide the gradient, it works faster. But this is not any complicated function, so we can ignore it. Okay. Then the method, by default, uses Nelda-Mead. But the others, each of them will give you different results, usually, with some precision. Each of them also has its advantages and disadvantages as well. Yeah, so, okay. So let's stick with the neodymium. Then if I leave it like this, you take the first one. So let's leave it like that. Then lower, some of the functions have lower and upper limit. Neodymium does not need that. But if we use, let's say, BFGS, then it needs a minimum value, maximum value. So it's like the bisection method. You state A as a minimum, B as a maximum, then you search within that framework for the solution, so to speak. Okay, so this one, I'll take it off because we don't need it. But if we come back and we need to use LBGS, then we have to come back to it as well. Okay. Then Haitian, if you want the Haitian matrix, remember you can get that and use it to find the Fisher information. All those things, then you can. But for now, we can put it off. And then the control, we don't need it now. But we need X. And X will be our data we generated. Okay, so that's the key thing. So that this, remember that what we did, the function is X, alpha, and beta. We have provided alpha and beta as the pair. Okay, so another way to do this to make it easier is that we need to take out this inside it. So please, let's go in. So alpha is assigned pair 1. No, it has to be pair 1. And then beta will be assigned pair 2. And then here I can just put pair. Why am I doing this? It makes it easier for us. Other than that, sometimes you can get confused. So it means that this pair will now be assigned to the pair in there. Yeah, and then we move on. But when you get inside, it splits them into what? Into 2. So it means I need to rerun this. And then I run this again. And there it is. I get my maximum likelihood estimates. Convergence is 0, which means it converges. The function count, the value of the function, you see 5.06, the parameter estimate. Remember I took 2 and 3, but you see it now came closer to what? The 5 and 2. So it actually says within it. Okay, so that's the, and now we can check with the maximum likelihood at the moment, which one is closer to the parameter. If n is small, which one do you expect to be the best estimator? Theoretically. Which one? So whatever we are doing, we have to relate it to the theory, on this. Which one?
Bro, can you go there a little? I got an error here.
Up or down? Ah, okay.
Sorry, up.
Right. So the method I did not put. Okay, I can bring it here so that it's like this. I intentionally did not take off the. Yes. You're having issues. You have to check, especially the parentheses. So, it says there, so, unexpected symbol. Okay, so you haven't finished. So the parenthesis ends here, so you need one more. The sum does not have, you see now, once I do the shadow goes there. So you can rerun the function, this one. Rerun it. Now it works.
I'm seeing yours is also 3. Mine is 4 here.
Yours is 4. Maybe you did more.
Additional.
Yeah, additional one. That's right. So always when you do parentheses, you have to always check whether it ends.
Wow.
Okay.
I was replicating yours together. Thank you.
Okay. Okay. Please, have you gotten it? You've been able to run it. You've got your results. Okay. So now let's see. Let's go back. If you are finished, let's go back and check. We are going to simulate 10 observations. Then we find the moment. We find the maximum likelihood. Okay. So to find the maximum likelihood, we have to also mle.est. Okay, so, and then the moment, let's also name it mom.est, so estimate, so that when we finish, we can now get them together and see how they look like. So let's do only 10. So 10, just 10 observations. Then we generate our sample, then we find the moment, and then we also go here and find the maximum likelihood. Okay. Now when you are done, we can now get the mom estimate. So results. So no. So mom est. And then if I want the MLE, I need to put star here and MLE dot est, and then I put the par. It's only the parameter that I'm interested in. Okay. So this is how it looks like. Remember, we are interested in what? 5 and what? 2. What did we get? 3.41 and 3.26. So which one is better? Which one is better? 3.2. Are you sure? We want 5. So which one is better? Of course, the moment. 3.41 is closer to 5 than 3.24. Is that okay? Yeah. So the moment is performing better. Let's look at the rate. We want 2. We have 1.362 here, and this one is 1.36. So the moment estimator seems better. It's closer to 2 than that one. But this is just 1. If we want to do this, we have to perform this several times and find the average of it, how close it is to 5. How close is this one to 2, and so forth. Okay? So that's it. So let's take, so let me take it like this, and then I'm going to arrange them so that it makes it easier for us to rerun it at a go. So N, and then we generate the data, we find our mom estimate, and then we find what? The MLE. Okay, so I just copied what we've done. I don't want to be repeating what, so 10, I can rerun it again. So in this case, as soon as I can put all of them together and run, and I'm going to get my results and compare. So see, I also did generated, look at it. Mom estimate is 7.29, beta is 3.5. Look at the MLE estimate, way off. Is that okay? So when the sample size is small, so 5.6, now it's doing a bit. So you can increase it. So this one is on average. Each time we do it, there may be some new results and so forth. But it's usually unstable if n is small. Okay. Now if I change n to, let's say, 100, and I continue, you realize that there will be a bit of improvement in the results than previously. But each time you can check between the moment and the MLE which one is performing better and so forth. By theory, as we increase the sample size, we expect the MLE to perform better. Is that okay? Because MLE, as n approaches infinity, we expect n. But it's not every time you get. So this one, you see that MLE is better. This is closer to 5 than that one. This is closer to 2 than that one as well. But it's not every time. So it's still closer. Yeah. So and so forth. Yeah. So basically, on average, if you increase the sample size, we expect the MLE to do better.
And the mom that's when the
Size is small. Yeah. Okay. All right. So please do this. So, I mean, these are the sort of things we want you to do. So, how do you relate this to the paper you were given? You realize that they did the maximum likelihood, you write a function. Now we know that if we have a PDF, we can sum log of it, and then it becomes what? The log likelihood. Good. So in the paper, they also have, they generated a PDF, which is a long function, but you need to write a function for that, and then you find the sum and log of that function. And that, the density always takes the data, right? If you are doing maximum likelihood, then you need estimates of the parameters before you optimize it. Yeah. So it means that the paper, you have to also show, notice what beta, what is its range, or the domain of that, or in this case, what is the beta. If it's greater than 0, then it means you cannot go and take -2 as a starting point because it's out of that range. So you have to choose a starting point within the range of values of that parameter. That's the sort of thing we use over here. All right. Okay. Let's try and finish this with how to find bias in MSE. Now, what it means is that if I want to find the bias of the moment, bias MSE of this one, then I need to repeat this several times. Is that okay? How do I repeat this? Well, it means I need to form a function with this. Then that function will calculate the moment and the maximum likelihood, right? Okay. And then I'll get, let's say, arrange it in a data frame or a matrix, and so forth. Then I can find the mean, I can find the variance. What's the easiest way to do this? Well, I can generate the data in a matrix form, and then if each row is a sample, I'll go through each row like we did, and then it will give me the estimates, and then I can subtract, I can find the mean, and so forth. Okay. So for a start, we'll go through it by generating the data. Okay. Remember, I generated the data like the one we did now. This is 1,000. So if I do a histogram of it, it's just a vector. Oh, I think we did even up the data. So we can go there and histogram. Where is it? There. Okay, or scarce price, right? So, okay, it's not. I need to bring it down so that we don't worry about this. So, it should be data. XLab, not really. Just index. So let's see. There it is. So that's the data we're working with, right? If I go back and change it to 10, you realize that its density will not look like gamma because it's too small, yeah, to give you any function. Okay, so what do we do? So we are going to generate a data frame of data or samples. So I'm going to use a function called apply and sapply. So these are the so we use
So why do you put
these are comments. So comment. So because I give you this, I wanted to separate them so that each time you know what we are doing.
I mean those
Hash. So it's for comment. So I use it to design it. It's just a comment. Yeah, but I use it to design it so that when I send you the code, you know that okay, this part you are doing this part you are. Otherwise, it will just be
like comments.
use like a heading,
Like a note. It's just
a note, yeah,
information.
yeah,
So it's not a code that is
running, yeah.
So if you don't put it.
Yes, it will give me an error.
Yeah.
Yeah.
You can identify that.
Identify this one. So like generate data, it is telling you that at this, what is
So
go.
how many of these?
You can use any. It needs only one.
Will work.
Okay.
Yeah, but I need to design it so that when you are going through the course, it looks easier.
Okay.
Yeah. So if you look here, this is like, you see this one, it's a practical case we are doing, right? So this one of my PhD students. So you see each of them. So it makes it easier when you are putting this in a thesis. Everybody knows what each of them is doing. Yeah. So that's why. So comments are very good because you'll be working with people.
Okay.
Yeah, you
Rob,
can.
This is
Yes.
Rob,
Yeah. So you see each. Yes.
I saw a huge chunk of. Is this someone's model?
No, that was to do data manipulation.
Okay.
Actually, it was my TA who did this. He was very good. So we have a data and then we have to rearrange it. So we use mutate and so forth and add some and so forth. So for example, the overtime, we wanted to know weekend overtime, Saturday overtime, Sunday overtime to be another variable. Yes, so like that. So he wrote that. I showed him, okay, we want to do this, and then he was able to.
How different is R from Python?
They are similar.
Because I've seen that some of the codes.
Yeah, some of the codes, yeah. So when you use the two, sometimes you get a bit confused, yeah. But you get it. You get it. It's not yeah, so that's it. So comments are very important to help you understand stuff. So we'll use a apply family, and I have a YouTube video on this. So I'll entreat you to look at it so that you understand how apply, S apply, L apply. There are so many of them. Apply, S apply, L apply, T apply, PA L apply, a whole lot. MCL apply. Yeah.
I've subscribed to the YouTube.
Yes.
And the videos I see so far, I've seen one of probability distribution.
Yes.
Another one about the data structures.
Yes.
But the rest are ACU kind of type in terms of the titles.
Oh, okay. So because I teach different courses, so usually if I up to 60, then is the group I made you join.
Okay, that's 602.
602. Yes, and then you will see Act 302,
Yeah.
and then start 240. So those are the core schools.
So
And
which one would you recommend for us?
Us.
oh, any of them if you are
I can
learning.
read them all, but
You
I
da-
don't know. And then there was one, your tone
Voice
so
was
down.
down.
So down. I
I also
increasing
I
the
increased the
Volume and it wasn't
Now,
coming.
I
Yeah.
went to check the comment and someone was
Comments,
complaining
okay.
about
So
it.
I think I started, usually I wasn't recording, but it was the COVID time.
Yes.
Then I realized, oh,
It's
then
good.
it's good,
Very
yeah.
hard
So
time.
then the students even like even more than the classroom one.
Yeah.
So
Take time and-
those that I sat down to do it on my own, then the voice came faster. But I realized that when we come to class, we also want to know what is going on. So I started recording it in class. So sometimes I go and stand with them and I will be talking, but the laptop is not with me. Yeah, because usually it's now that I can't walk properly. But I go around, especially when there are many. I go around, so sometimes when I'm sitting here, you hear the voice. But somebody will get a problem, then I stand up, I go, then I'll be talking to the class, so you hear it. But those in class will, and they still seem to like it, so I put it there. But this one, I recorded it, so it's this particular one, yeah. They apply, so when you go in and you search through, you see they apply family of functions, and then you go through it and so forth. So let's see. So,
I've not seen one on functions.
oh, I have done so many. Because I teach it all, and each time I record it. But there's one that I sat down and recorded. I think I need to find time and group them, yeah. And so forth. There's not, yeah, yes.
But sometimes, the truth is that I want to start from fresh.
Yeah, but there's no sequence.
Yes,
Yeah,
that's
there's no
the
sequence.
problem.
Yeah.
So,
Why
I-
don't you number so that we can...
I need to get a TA to assist me. It's the time. What I think what I need to do is to so I need to record and then get a playlist.
Yeah.
Yeah, but
So I
you
need
see
part
this
one,
one I'm
part
not
two,
here
part
part two.
three.
Yeah, so, but I need to be serious. I'll do it. Just that time. Oh, it's on YouTube.
It's on
Yeah.
YouTube.
Check for
Yeah, yeah, it's on YouTube. So it becomes easier for students. But when I'm teaching them within the semester, I record it every week. So for the class, they will know. But usually they go there to download.
Yeah, so even I wanted to even suggest that even these things, as we do like this,
Yeah.
you could be recording.
Oh, yeah, I record, but now I think okay, it's recording. So this one is recording.
And
So when I finish, I'll send it to you.
Okay.
Usually I do that. Yes, yeah, yeah. So the ones that I did with you, they are all on YouTube. The 60, yes, exactly, yes. Yeah, I do that. Yeah, it becomes easier. So this I'm recording. No, you have to.
Hey.
No, when you are here, the questions, yes. Well, sometimes I haven't really been answered questions over there. But because I meet them, if they watch and they have a problem, we meet in class. But I have to be active over there and check when somebody asks a question and so forth. They say I can even get money from it, but because there's over 40,000 views. As of now, yeah.
So you've not gotten any money yet?
Oh, I haven't even bothered to.
He hasn't, he hasn't monetized it.
I need to monetize it.
I know
Yeah.
you already...
Oh, no,
Hey.
nothing. I'm just doing
Monetize, you need a minimum of 1,000. Currently, you have 820.
20. Oh, I have not been active because level 100, if I record one video for them, I used to do it. Yeah, but it will be because they are over 1,000. So,
The videos you can segment them.
yeah, to be
sections.
sessions, yeah. That's what they were saying. I haven't, it's not professional as for that one. It's just class, go and sometimes even my jokes and so forth are all in. Because it's just, but I need to take time. When I sit and record, that one there are no jokes. But in class, I joke with them.
So,
So,
what I've noticed is that
yes,
yours is very different from others.
Yes.
So we download our programming from others.
Yes.
Data science.
yes, yeah.
If you see, yours is more, it's like more detailed, more complex. They do the surface.
Yeah, there are certain things some of them are from experience, and I do work in computational statistics, so I do all this. If you check, I have programs running now. I'm done with the simulation I'm doing, so the computers are free. But other than I set it so as you are doing this, you encounter this, and those are the ones I used to teach.
And Prof, you do that, you can make a lot of money.
Yeah, but we will see.
You are looking for money.
Yeah, I have to. There are certain things I'm doing now. Papers.
What other people are. I mean, if you are
Yeah. I mean, the one who taught me how in Stellenbosch. He is Leroux. I need it too, but yeah, time and other. But I'll get it done. Yeah, I'll get it done, and then let students really like. So let's see. Okay, so they apply. In simple, it works usually on so data frame rectangular. So what we are going to do is that we are going to use. We will need the number of repetitions we want to do. So we are going to do that 5. So for a start, I want it to be simple, but we have to increase this to like 1,000 so that we get 5. Then, so let's name that math data. So it's like a matrix data, right? So how do I do it? I'm going to use what we call the supply. So this is a supply function. So that it can take a list and then act on a function. So that list, I'm going to say repeat. So 1 to R means 1, 2, 3, R is 5. So 5 of them, right? So what is my function? My function takes I. So it means that when it takes 1, I will be equal to 1, and then it goes in. Then all what I'm doing is I just generate observation from a gamma distribution. So I'll come here and copy this. So what is this doing? It's simple. It takes, let me also put the sample size here. Sample size is 10. So we are going to generate samples of size 10. How many times? 5 times. Okay. So let's do this first. And then 1 to R. You see 1, 2, 3, 4, 5. Is that okay? All right. So the first one, let's do it and see. So if you come here and you check math data, you see it's numeric 1 to 10, 1 of 5, which means we have 10 rows, 5 columns. What does that mean? Each column is what? A sample. Is everybody okay with this? Each of the 5 columns is a sample. So let's see. So first column is a sample. Remember our sample is of size of 10. And then we repeat it all 5 times. Yeah, so that's it. So you see that it comes in handy. Just one, and we have several of them. So it's our repetition. So now if we take each column and we put our function in there, what is it going to? It's going to give us the estimate of what? The parameters. The one that will give us average close to the 5, and the 2 is a better estimate. And we can increase the sample size and so forth. Okay. So that's our sample. But now I want to put all this also into this. I'm going to put it in a functional form. So I call it estimators. It's a function. That function will take in what? X, which is the data, and then it will take in power. Remember that the maximum likelihood would need parameters, but the moment doesn't need anything. Okay. So what do? We put that one here, Okay, then this one has to be data. Right. Okay. So data. Uh, yeah. And then what do we want to? So our tab will be, we can use a list or we can use a data frame to also, whichever one we want. So maybe data.frame. Okay, so moment will then be equal to what? Mom est. MLE will be equal to what? This, and then we select the par. Oh. Ah. We select what? Par. Is that okay? Okay. Then we return tab. So it means that if I run this, I should be getting all the two estimates, right? So let me see. I just want to check first. So I call math data, then I choose the first column. Is that okay? After the comma, that's the first column. Then par, I give it, let's say, 1 and 7, so to speak, just to show that we can change the value. So let's see. Okay, so you see, we have it. You see the way the outcome is. The moment estimator, the alpha dot hat is what? 4.93. Beta hat is what? 2.16. When we go to MLE like this. Now, if I repeat this over time, I'm going to get different this thing and so forth. Okay. So because you are new, I need to collapse this into a vector. Then we name it. Other than that, when I want to work on this, we now have to extract, because it's in I'm going to get small matrix made a 2 by 2 matrix 1,000 times. And then I have to now write a function that will go through each of them and select the alpha hat. And then I select, and it will be difficult. Now, so what I'm going to do is that this, instead of the data frame, I'll get a long one. That one, it will just be a matrix, and I know that one is alpha hat of mom, this is that, and so I'll name it that way, and it will make it easier. Okay, see. Let's see if this one will work. Yes, you see now is like this. So I have mom alpha dot hat, mom beta hat, MLE1, MLE2, those kind of things. Okay, but I can name it to make it easier. So names. Oh. Tab. So I don't know what you want as do you want the MLE dot alpha? Okay, we can do it MLE alpha. Maybe mom alpha is okay, otherwise it will be too long. Like this. And then mom beta, right? And then so I can copy this to paste, and then I change the mom to what? MLE. So I can bring this one here to make it easier. So this one I have to make it what? MLE. This one too, I make it what? MLE. Is that okay? All right. So now if I do this again, you see, like this. So this one, when I repeat it 1,000 times, I'm going to get a matrix made up of, let's say, 1,000 rows and so forth. Okay. All right. So how do we go about this? Well, we can also use the apply function. Okay, and then use it on our, or we can also use the lapply function and move this 1, 2, 3. So the column 1, 2. So there are several ways to do some of these things. I think that will be better. So let me see. Estimate is. Then I can use the lapply. Oh, sorry. Or even the S apply again. I think it will be better because you know the S apply now. So S apply. So it will still be 1 to R, right? 1 to the repetitions, isn't it? Good, okay. Then we call our data. So we need function here, and the function is I. So it should take each of them and call this I. And each time we are using the same, what do we call it? The same alpha, beta. Okay. So if I do this, yeah, it did. And then you see numeric 1 of 4, 1 of 5. So it means each column is now this is it. But usually you want your name to rather be, so I would, please look over here. So this is the outcome. But usually you want your variables to be on the columns, and then the repetitions on the rows, not the other way around. So I can go back and put everything in T function, which is what? Transpose. And when I transpose, the rows will become columns, yeah, and so forth. So I'm going back, and then here, I'm putting everything in the T function, small letter T. And I'm going to do this again, and you realize that when I click on it, I now have it. It makes it easier. Okay. So that's it with how we can get our estimate. So here, compute estimates for each repetition. Each repetition, or each sample, maybe. Each sample. Okay. All right. Okay. Are you making progress? Are you making progress? Okay. If you are not clear with anything, you let me know. But at this stage, we are borrowing on the things we learned. Yeah, the only thing is this apply from this. Please take your time and go through. I think it's just about 30 minutes or so. It's very important, and it helps you to maneuver your way through, especially with data manipulations. So now the next thing is that we now have repetitions of the estimator. So we can now find bias quite easily. And we can find the mean square error because we know the actual value. So, but how do you find it? You have to also write a function. So R is just function. Once you know how to write a function, you are good to go. So we write a function to calculate bias. How do we do it? How do you calculate bias? You need to put in theta hat, right? And then you find mean of the theta hat minus the theta you are estimating. That's all. But what about the mean square error? Well, the number of repetitions, we need to find each of the theta hat. We subtract the theta from it, we square it, we find the average of it. So what is it? We can find mean of the average square, that's all. Sorry, the square deviations. Yeah, average of the square deviations. So that's it. So let's try and do that quickly, and then I think we can close so that when you go, you can go through it. Okay, so now function to compute bias. So I'm going to do it individually, then you do it. So bias dot fun will be equal to a function. So what do you need in order to compute this? So all this from basis, what do you need? If you are writing a function, you have to know at hand what you need. I need bias is the expectation of x minus what? Sorry, the expectation of theta hat minus theta. Okay, so I can do theta dot hat. That's to show that I need theta hat, and then what? Theta. Okay. So how do I find this? It's just the mean, because the expectation of what? Theta hat. Expectation of theta hat is the mean minus what? Theta. Okay. So this is it. When it's a function like this, you can just, this is okay. If it is one line of code, it's okay like this. You can write it on, but because I want you to, I can also bring it over here. But it means that if I am writing this, I need to select all of them at a go and run. You know, I'm not putting any curly bracket. Ideally, there should be curly bracket, but because it's just one line of code, I can as well leave it like this. So I can do this, and that's it. Is that okay? All right. Okay, now I need to calculate the bias. But remember the way you did, so if you have a data, you have to be careful. Remember, we have each of them, the first column is the mom alpha. The second column is what? The mom what? Beta. Is that okay? So it means that my theta hat, you have to be careful how you use it. Otherwise, it is going to take, when it's supposed to subtract 5, it's going to subtract 2. Is that okay? And there's no need to be also be going around each of them and be doing that. So you have to find a way around. So we can still use, so if I call bias fun, I can, theta hat should be equal to, let's say, what was it? Est.
So it means that the R doesn't have the bias function in it.
No, you have to. So, oh, this one doesn't have a, I thought it's a data frame. Okay, it doesn't allow us to. Is it a data frame? No, it's not. So it has been a, so what do we do now? I want one that will be easier. If we use apply, it's going to take each what's the way forward? So the first one is 5 and the third one is 5, right? But the second and fourth are also 2. What I don't want is repetition. So if I'm doing it, I'll find a way out. That's the other one I didn't want us to do because it takes so much time. But you are a bit of beginning, so it's okay. Let's look at it. So what we can do is that we can also group them into bias. So into the, one other way is also group them so that you have a matrix that is made up of only 2 columns, which means you have only the alphas together and then the betas together. So that one, when you call the function, you only need that theta hat. I think maybe we should do it that way to make it easier for us, so that I can use the apply function too. So separate, separate alpha and betas. So how do we do that? So alpha dot hat will then be equal to, we have to call the est function. Do you remember this? We talked about what do we call it? Subscripting. So remember the alphas are the first and third, right? Is that not the case? You are not following. Look over here. This is it. The alpha, you see the mom alpha, and this is with the first and third. Good. So I'm going to call this and put in 1 and 3, which means take the first and the third column. Okay. So this one, if you see mom alpha, MLE alpha. So it means that I can also get a beta. 2 ways to get a beta. So I can negate this, which means take out the other one. Yes. Or I can also just put in, exclude 1 and 3. So I can also put in 1 and 4, and that's it. Okay. So that's it. And then let's look at the beta. So there it is. ML beta. Okay, so now we can then apply. So if I have it this way, then it becomes easier for me to use the apply function to get the. We will close very soon. Okay. Don't worry, we are about closing. So it's so easy.
Since 4 a.m.
Since 4 a.m. It shall be well. When I finish, I have to go and then now sit and do another work. So easy. You will do it, don't worry. You have to combine it with families.
That's why the old man left us.
I was thinking that I should come back.
I mean, we can go to back now. Old man like the one I see before.
So let's see. This one, it takes the theta hat. See the way I'm doing it. So if you take alpha hat, 2, it means take each column. When you take the column, so the x is the theta hat now. So I'm going to call this theta hat and then assign x to it. But the theta is, what is the alpha value? Is 5. Is that okay? So now this will be 5. And then I do this. Now I can get the bias for mom and then MLE. So you see this one, the sample size is small. So look at the moment estimator.
0.5.
It is giving us a better bias. Of course, the bias, the measurement is to get to 0, then it's unbiased.
Okay.
So if it is larger, it means it's way up. And all of them are overestimating the parameter because they are all positive. Yeah. Okay. Yes.
In this case, the movement is better.
Better. Good. Yeah. And the sample size is small,
So when
10.
the sample size is small.
Yeah. Usually you get that. But remember, we repeated this for only 5 times. You need to do it 1,000. When we finish, you can just go in and just change n. Then you run to, yeah, and then it gives you those things. So what we are doing is what you see in the paper, that the n, then they are increasing n. So you do all this and then you get your table and do it. And whatever table we get, we can now print it into LaTeX from R straight away using X table. Okay. So now I can also do beta, right? beta, bias beta, sorry. I'll leave MLE to you. When you go, you can do it. But the beta, the theta is what? Is 2. Is that okay? But everything else is, and the alpha hat should be beta hat. Is that okay? Please, are you following? Yeah, okay. So we do this as well. And then the beta, you can now check it. So the mom is still doing far better. Yeah, like that. Okay, so that's it with separate alpha and beta. And then compute bias. Compute bias. Now, when you are done, you can get a function for the MLE. It will be around the same thing. So function to compute bias. I can copy here. I'll just write the function. Then when you go, I'll send you the codes anyway. And then when you go home, you can. So this function to compute MSC. So how do you compute MSC? You need this as a mean, but it's going to be mean of all this squared, right? Do you agree? Yeah. Yes. Mean of the squared deviations, like this. Okay. So I need to change this to MSC fun. Okay. So like this. Okay. I can change this. I will finish early. Maybe you will not, but I'll send you the code so you can check. You can check it. So all I'm going to do is to change this to MSC, and then I change this to MSC. And here, instead of bias fan, what do I put? MSC. So everywhere I see bias, I put what? MSC. MSC. And then I run it. And I check MSC alpha. So mom is still doing well. MSC beta, mom is still doing well. And so forth. So if we, what you need to go back to do is that if you start from here, where is it? That way. Here. So this one, you don't even need to rerun it again because you, so if you want to do everything again, you copy this and that. So repetition, I'll just, so you see we are doing this one after the other, but at the end of the day, you have to put all this together. Later on in your thesis, you may be using this, you sit at home, so you can't be interacting with the program each time. So that's why the other one I showed you, you have a whole lot of code. So when we run it like this, or if I come, I don't know if my own is gone up, but if I come back here, all I'm checking is to see whether the function has run. If it has run, I only see graphs. So if you look over here, I think somebody has, maybe, yeah, somebody has, somebody is also running the program over here. But mine, when I come, it's just graphs, then I just copy them. Yeah. So whatever we do, the end point is that you put all of them together. So if you put, it is a gamma, you put in 5 and 2, and then repeat it, and sample size is 100, repetition is 1,000, it will run and give you the MSC, because that's all you need, MSC and bias. Yeah, and that's it. Okay. So if you want to put all of them together, what you have to do is this. So you get your data. When you get your data, what next? You don't need a bias function again. You compute estimate, so you need this. You don't need a function. The function needs to be run just once. So if you have run all that, you don't need it again. So I'll send you this. You compute for each of them, and then what next? I think after that you separate them, right? you don't need the bias functions because you have already written them. So you separate them and then you compute bias, you compute MSE. So let me just copy and then I'll delete those we don't need. And then it becomes easier for you now to just rerun them. So this one we need it. We don't need a function to compute the so this one was MSE. I did not change it. I have to go back and change. Compute MSE. Alright, so at this point I think you can just look at it. I'll send it to you so it's not a problem. Compute bias. So that's it. Okay. So I'm going to just rerun some sample of, let's say, a simulation to check the bias and MSE of moment and maximum likelihood estimator for. So what I have done, we can put all these together to now form what? To form a function such that you run it just once and then it gives you everything that you want. So let me see. Okay, so let's see. So I start from here. So I'm going to increase the repetition to 50. Is that okay? N is still 10. So I copy all this and run. Okay. So when you come here, you see the statistics. So the bias of the alpha, you see mom is doing better in each of them. Is that okay? Yeah. I can increase it to 500 as the repetitions to, let's say, 5. As I said, ideally it should be. And as you increase it, you realize that it will take a bit of time and we can measure the time. Okay, so I can measure the time. How do you measure the time? Let's say TT is, there's time in R. 6.time. This. So I can check the time now. It will give me the time 1848 GMT, right? Okay. So when I do simulations, at the end of the day, I check the time. So 6.time minus the time I started. Yes, so I time myself TT. So if I increase, let's do this, it would, okay, so the time was 0.44 seconds, right? Okay. Yes, so let's change it to 50. You realize that it will reduce. It was 0.44. You see 0.055. Okay. Good. I'm going to, if I 100 and then I change the sample size to 100, you realize that it will take, because the computer takes a bit of time to compute it. You see now it's hanging. Yeah. 1.6.
But it's still very fast.
Yeah, it's still, because this is not any computation. Yeah. So the one that, it's not any computation. But I have some that takes a day. I've done some that takes a month. And during my PhD, it will take a month. Oh, but there are some that takes over 3 months.
Bro, what if there's a part failure?
And then, yeah, so in 2015, I came back to that. I had to go back. Yeah, because I'll do it and then in no time it goes up. Yeah, and you can't use laptops for a PhD simulation. Yeah. No, that's why we have these ones. But we don't have a generator that, so when it goes up, it's up. They can, there are UPS, but they won't take that much time. So those are the challenges we have here. But for universities that are really investing in, even Workday have some, and they usually allow, I've used it before. I don't know whether they have changed their system. Workday and Workday. They have funding, so they have HPC, high performance computers.
So why is it that
funding. Yeah.
Do that.
It was funding also.
No, they even need more funding.
Exercise council. And the
Yeah,
Minister of Finance.
So, Prof,
And finance gives them.
No, they have everything is donor funding.
Even if you work for them,
They
if
chop
you
the
work
money.
cry, they will not pay you.
They drop the money, they will. I mean, civil
so if you are
service.
even experiencing it,
Yeah.
Prof, then I'm so isn't there a cloud system where maybe you can run the model on a cloud system?
Yeah, you can. Our studio has some, but you need to pay.
Okay.
You can use it even once you are doing. You can log into our cloud and do it. Yeah, but if you need to do more, you need to pay. And have access.
Will they charge per month or per process?
I think maybe a year. They usually will have maybe a student version.
I think we will more.
But I've used, when I was doing my PhD, I used a Huawei one. Professor Wandaris, they have a very, it's very fast.
So it means that when we are writing exams, we can't be exit.
Yes, but this one I don't really, it's PhD, so I don't really, I'll examine you, but I'll give you a paper like this, you go and complete, then you come and demonstrate it to me, then I ask you a question. So I work one-on-one. I can bring maybe other people to help me grade it. That's what I do. Not me alone. So Dr. Okran will be, Isaac can also do. Yeah, then you demonstrate. So we want to see whether you did it yourself. Yeah, you understand the process. But it's important. I mean, if you are holding a PhD, these days you cannot say you can't program. And hardly will you get somebody to some you may get, but when it comes to PhD, because you are so limited, you have only a few people who understand really what you are doing. Yeah, so the training here, and this is, they are very important, basic, but you build upon it. And that means they apply family, they comes in handy. You have to, maximum like you, I think now we know the concept. Yeah, so it's very important. Usually maximum like you can't do without it. Most cases. Yeah, method of moment. So there's a paper that I reviewed for a journal. I'll try and get it and send it to you. It also implements several methods. So it's one of the papers I will want you to also go to. I don't know whether they have published it yet. So today, this is a paper I am reviewing, and I think the deadline is today, so I have to stay and do it. So double till so and so, but I have one. Yes.
Peer review journal.
Yes. So this is Communication in Statistics. Simulation is one of the top journals in statistics. Otherwise, I won't even waste my time. Me, they have rejected my paper before, but then they will come back, review a paper. The acceptance, what was this journal?
So the review process, you need to go through everything.
Yes, you have to.
Line by line.
Yes. You read and check everything to make sure it, and you are not being paid for.
Hey.
No, not at all.
But then you'll be in good standing.
Yeah, so that's the only. Yeah, so it's part of academic, your academic.
So, what of those of us who don't really want to be in academia?
Then you won't. But once you start publishing, people will read, and then the editors will know, okay, this person is good in this area. Then yeah, so when they bring you something to review, especially a journal, then you know that you have arrived. They don't pay, no, nothing at all. No payment. And the irony is that some of them even take money from the people. Yes. Oh, there's and no, some take, others do not. Yes.
Please, would you regard Taylor and Francis as
Oh, if it is in Taylor and Francis, then it's good.
my paper is
Hey.
Yeah, but the Taylor and Francis is, what do we call it?
Class B or Class C?
No, it's
Applied.
no. The paper I'm reviewing, I've forgotten what to use. It's like a database, so to speak. Yeah. So there are so many journals in Taylor and Francis. So this one is also in Taylor and Francis. But it's a journal of communications in statistics, simulation, and computation. Others are. I've forgotten the journal I did this paper for. Journal of Series, Mathematics, Natural Hazard, and Sanka.
So, Bob,
Yes.
in case you are ranking the journal, which one will be number one, number two?
They have, if you publish in JAMA, JAMA or JASA, Journal of the American Studies, JASA, I think that's the top.
Top.
Yeah, Journal of American Statistical Society.
I learned Africans, we have journals.
We have, like,
they are not very credible.
yeah, some journals are not credible. That's why I said, if it's not this, me, I won't worry myself. You are not giving me money, so why would I waste my time on this? But we also do it because it helps you to get collaborations and also students. So once I review it and I see something good in it, I can tell my student that, okay, there's this paper, review it, you find something else to do. So in academia, you are a bit of forced to.
Readings
I
are
understand some of the journals.
Yes,
that
yeah.
lecture
Yeah.
and publishing when you get promotion, but some don't get.
Which one?
Some of the journals, if you are a lecturer,
Yes.
you publish in some of the journals.
Because
you get promotion.
because
But others-
some of them are not, as I'm saying, they are
Mule journals.
yes. So estimating the
Annals
thing.
of Institute of Statistics.
Yeah, so this one too is a very good.
Statistical mathematics.
Using a double till. Oh, this is the same paper. Yeah. Okay, I'll search for it and send it to you. Or maybe, I don't remember the journal, but I get Journal of Applied Statistics. Oh, if I have misplaced this, it will pain me. Because it's a very good paper which will help. Okay, I'll search for it. Just remind me, because as for me, when I leave, it's like everything goes
Well,
to.
in case I'm reminding you, what should we say?
And you say the paper. Oh. It's a very, because they compare so many methods, and it will be good you have such a comparative paper for your. But I'm surprised. I thought it was Journal of Applied Statistics.